Yesterday, my physics students performed AP Experiment 3, a video analysis of moving objects. I tried to film it, but somehow the video got deleted. So what we had them do, we were looking at a cannonball, and why does the cannonball travel at 20 meters per second across the x-axis? Well, it travels at constant velocity because once it leaves the actual cannon, there's no force acting on it. So the velocity is constant. So what we wanted to do was determine the force acting on the object inside of the container. So the first thing we needed to know was the time it takes the ball to reach zero velocity and the height. So the thing went past the meter stick, so we just measured the length of 100 centimeters and the time it took for the object to get to this point. We had it on video. Isabella Kerpenstein got us that from the tablet, 1 second per 100 meters. So it took 1 second for the object to travel from here to here. Next thing we needed to know is the speed or velocity of the ball as it left the container, and we used the Go Motion Veneer Pro to do that. And Medina came up with the time or the velocity of 8.7 meters per second from the GoPro machine. So that would be the constant velocity. So to get the acceleration, we took the constant velocity times the 1 divided by 0.81 seconds. How did we get that? Well, the length of the inner container between this point here and the top, when you put this object in, this is what was shot, was 1.8 centimeters. So we take 1.8 times our conversion factor, and that gives us 0.18 seconds. So if we multiply the constant velocity times 1 over 0.18 seconds, we will get meters per second squared, which is the acceleration of 48.3 meters per second squared. And we multiply that times the weight of this right here. So we just took this, put it on the balance, and you'll see that it's around 19. This one's 21, the other one weighed a little bit less. So that's where that mass came from. So if you see over here, the mass of the projectile was around 20. Divided by 1,000 gives us 0.01932 kilograms. So force has to be in kilograms. So you see your kilograms times your gravity gives us the normal force of 0.189. So if we want to find the net force, we're going to take the force of the propulsion out of the cannon, which is 0.933 minus the net force, correction, the normal force, which is right here, and we get our net force. So I'm just documenting this, so if I ever do this again, it's a really good example of where the force occurs associated with the acceleration. So the acceleration only occurs inside of this container. Once it leaves the container, it's at constant velocity because there's no force then acting on it. For oxygen. Now, I've given this to you already. We talked last week about how helium has hydrogen structure within it.
Are we supposed to know how to do this?
Yeah, we taught it last week. I know you're forgetful. Yeah.
I wasn't here Monday.
Now,
Marley,
Marley, from last week we had you color code the periodic table. If you have it, I'll take a look at your work. So the S is colored blue here, associated with the blue S here. So when we say S, we're talking about the shape that the electron will occupy.
oh, that's what we're doing?
We can put 2 electrons in each shape. And it's actually, you need a 2 right here. That is correct. Now, what do the 1s and 2s associate with? Yes, the periods in the periodic table, there are 7 periods. So you'll never have an 8. You'll only see a 1, 2, 3, 4, 5, 6, or 7. So right here, this 1, Amari, this 1 corresponds to the first period right here. And the 2 corresponds to the second period. Is everybody clear? Anybody question on that? What the numbers represent? Okay. Let's take it one step at a time. The 1, the first number, the 1 corresponds to the first period. Does everybody see that? That's the first period. The S corresponds to the shape. That's where the electron will be found, in that shape. The number next to it, or above it, like I should say exponent, tells you how many electrons you have there. Last week we learned about hydrogen has just 1, so hydrogen equals 1s1. There's one, only hydrogen can be 1s1. And then we have helium equals 1s2. So oxygen has helium structure within it, and it also has hydrogen structure within it.
What's the number below?
Below where? That's the S.
Right here, 1S.
Okay, we haven't talked about that yet. We'll get there in a second. Good question. Now we're doing potassium.
Orbital similar to hydrogen. This allows us to describe arrangements of electron and atom using specific rules.
Now remember, when we're doing these electron configurations, that we're building on what already works. So we have helium at 1s2, and then within helium, if you look in there, you're going to see what hydrogen's doing. You can see the electron following a similar pattern. So much of life is about recognizing patterns. We do it all the time to make new things. We wouldn't have airplanes if we didn't notice birds fly. That's called noticing a pattern. So if you don't pay attention to patterns in life, then you tend not to be successful, like in business. Because if you're not paying attention to specific patterns, that's when you go out of business. Sears. Once the energy level is filled, we can use something called the noble gas shortcut. All of this right here represents argon. So it's the noble gas. And then we write the last electron associated with the element, which is potassium. And that's the symbol for potassium, or the electron configuration, that is, for potassium. Okay. Now when you came in, I gave you this sheet. And at the top of the sheet, I want you to write, next to the 1, that is the principal quantum number. How many principal quantum numbers are there on the periodic table? Freddie? How many principal quantum numbers are there on the periodic table? Yeah, you can see there's 7 periods on the periodic table. You're not going to see 8 periods. That means there's 7 rows. Does everybody see that? Anybody not see that? Raise your hand. So that's what this represents. It represents the period number. What we call it the principal quantum number. Now the letter next to it represents the principal quantum variable. So write principal quantum variable. Like x is a variable, y is a variable. So they've got some variables. principal quantum variable. That's a lot to say. Write that down. Principal quantum variable. Now, what this corresponds to would be the first energy level you can place 2 electrons. That's the maximum you can place in the first energy level. Why? Because there's not enough volume. If you're looking at a gobstopper, the one that's closest to the center has less volume compared to the one that's on the outer part of the gobstopper. There's more volume on the outside of the gobstopper compared to the inside. Is everybody clear? So because there's very little volume, you can only put 2 electrons there. Now we're going to scroll down here to the 7th period. How many electrons can fit in that volume? We're just talking about that 7th outside gobstopper layer. Yeah, 98. Now typically there are not 98 there under ideal conditions. How many are typically there? Well, if you look right here, do you see this is a 3? If you have this table out, that's a 4, 5, 6. That's the periods. This is a 4 and a 5. So there's only a little bit on the 7. Right here, that's 2 plus 6 is what? 8. So normally under ideal conditions, you're only going to see 8 here. But 90 can go in there, 98 plus 90. If the conditions are right, you know, a lot of things are affected in life. You know, you got pressure, temperature. A lot of conditions can change to cause electrons to move around. And they're going to move around the most on the outside. This is kind of like when the Hulk goes Incredible. And he gets all crazy and rips his clothes off. You ever seen Incredible Hulk? It's a Marvel Comics Hulk. It went Hulk on you. So that's kind of like the 7th period. It went Hulk, and you got 90 extra electrons there. That's a lot of, like, what do they call it when you get excited? Somebody runs over your foot and you're trying to survive. Your what? Kicks in. Yeah, your adrenaline. So there's probably some adrenaline happening in the 7th period. So in your book, they'll talk about energy increases in which direction? To the 7th period or to the 1st period? Energy is increasing in which direction? Toward the 7th, yeah, because you have 98 electrons that can go there. That's a lot of electrons, that's a lot of energy. Does it make sense? Anybody have a question about that? So they're introducing the G shape, the H shape, and the I shape. And they got them shown right on the sheet that you have here. They've labeled pi and sigma SS and sigma PP. I just went ahead and put GHI associated with them. Now you don't see those shapes on the periodic table. Why? Why don't you find those on the periodic table? See, on the periodic table we got S, D, P, F. Why not on the periodic table do you see the GH and the I? Why don't you see those on the periodic table? Davis? Because they're not considered to be normal conditions. Under, let's say, different conditions, you can get these. But the normal conditions, you're going to find these. These are, if you look right on the one I gave you at the bottom, I should have taken this one up there. You can see the ideal electron configurations for the elements. This goes all the way to 118. So this is under ideal conditions. You're going to see the SPDF. But that doesn't, what you're trying to show you here is that the electrons can move around. And that's what you're seeing right here with the 50 and the 72 and the 98. They can move around. Like on the 5th period, you can get the G. You can get more electrons in one location under various conditions. And that's what we try to do. We're trying to predict what? We're trying to predict patterns. Because if you can predict patterns, it goes back to business. You can stay in business if you can predict patterns. If you can't, then you're going to have a hard time staying in business. Patterns, things do repeat themselves quite frequently. Most people just don't pay attention to it. Associated with different types of shapes. So you have the SPD, right? So you see right here there's a 4. Does everybody see the 4 on this table? You should still have this in your notes. So the 4 means that there's a D there, and then there's a 4 right here, means there's an F there. So the SPDF means that there are 4 sub-level shapes associated with the 4th quantum number. Now how many are associated with the 5th? Anybody see that? So you've got 1, 2, 3, 4, 5, 6 associated with the 5th. It's on your paper, isn't it nice I gave it to you? And how about with the, so we got, with the 5th we have, we should have 5 there, I'm thinking. Yeah, we have the S, P, D, F, G. 1, 2, 3, 4, 5. Yeah, so there are 5 there. Everybody see that? These are the 5 different sub-levels associated with the 5th period, or the 5th quantum number. Kind of a lot going on there. So you might want to write next to that in the book, they're referencing it. That's the sub-levels. These are the sub-levels right here. So you have 4 here. Does everybody see 1, 2, 3, 4? On the 4th, there's 4. Any question on that? So I'm pointing out the 4 is right here. 1, 2, 3, 4. You see here in the book with the little black boxes there. Right here, the 4.
Electron is called the element's ground state electron configuration. 3 rules or principles.
Energy. So we're going to start with it. The off-ball principle says fill lowest to highest, start with the 1s. Can hydrogen exist as a positively charged ion that is just a proton floating around? Can you have a H plus ion? Yes. Where would you find it? In water. Have you ever heard of acids? So if you take something like hydrochloric acid and you put it in water, you're going to have an H plus ion floating around in water. So an H plus ion means it doesn't have an electron. It only has a proton there. So this is going to be filled first, the 1s1. And it's associated with the pattern. So if hydrogen is doing this, all the other elements will follow this pattern because they're built on hydrogen. If you look inside of lithium, you're going to see hydrogen. You look inside of gold, you're going to see hydrogen. So this is called a pattern. So if you notice these patterns, it's much easier to then develop new products. That's why we've been able to develop such new products so quickly. If you went back like, I don't know, just 150 years ago and you look at the different products that are out there today compared to 150 years ago, people are amazed. It's part of the reason why we have so much plastic in the ocean now, because we've been able to make so many different products. State. Anybody remember the Heisenberg uncertainty principle? What does the Heisenberg uncertainty principle state? Ben? What does the Heisenberg uncertainty principle state? Anybody remember? Okay, Trevon. Right, so if you don't know the velocity or the position of the particle at the same time, you're not going to know the origin. That is the line that it's following around the nucleus. So because of the Heisenberg uncertainty principle, you see electron clouds. Now if you went back to the 70s, they showed the planetary model, where you have electrons moving in certain origins around the nucleus. The reason why the origins aren't there anymore is because of the Heisenberg uncertainty principle. So that's important to remember, because you're looking at this. This is a lot more vague. A cloud is definitely more vague than an origin. An origin is more specific. We like specifics. Nobody likes vagueness. People want, I want like definite answers. Don't give me vagueness. Well, unfortunately, we don't have definite answers because of the Heisenberg uncertainty principle. Excellent. Nice job. That is correct. Electron by electron. So how are atoms built up? Yeah, they're built up by the protons. So the atom is... Yes, protons. You may call Emma Olivia. Yeah. Yeah.
She's my favorite.
She's a cool person. You're close, but that's not right.